Hello and welcome back. Today will be the first of 5 tutorials on open-ended AICs. And by open-ended, I simply mean that the chain has 2 distinct freestanding endpoints, as opposed to being a loop. Because don't forget, loops are AICs too. The links in a loop alternate just like they do with an open-ended AIC. Unless we alternate the links and thereby alternate the inferences, strong, weak, etc., it would not be possible to connect each link to the next, nor would it be possible to make any logical deductions about Sudoku chains. We touched on AICs way back in tutorial number 4 just to get started. But now that you are hopefully much more advanced in your Sudoku knowledge as a result of studying and mastering all the previous videos in this course, we are going to delve much more deeply into these chains beginning now. Because after all, they are the golden key to unlocking the very most difficult puzzles. Here is a brief outline of these next 5 tutorials. First, we're going to review the characteristics of strong links and weak links and the method we use to connect them in such a way that allows us to make logical deductions. Then we're going to look at an AIC type 1, which will always begin and end with the same digit candidate, regardless of which candidates are in between, and we will examine the 2 ways in which the endpoints can relate to each other. Then we will switch to type 2, which will always begin and end with different digit candidates located in cells that can see each other, and we will explore the 3 possible outcomes for these type 2 chains. Okay, let's get to it. I have to tell you, I get so many letters from so many people asking me all kinds of questions, clearly indicating that they do not understand the logic of strong links and weak links, and how alternate inference chains are constructed. They just don't seem to get it. So today, hopefully once and for all, I am going to make sure that all of you understand these concepts backwards and forwards, in and out, and through. I will explain how they work and why they work, okay? If you want to be able to solve the most difficult puzzles, it is absolutely imperative that you understand the logic of all this. The very first thing you must understand is that when we say something like, if A is false, then B is true, which is the formal definition of a strong link, this is a conditional statement, okay? A conditional statement. It is not a statement of fact. Rather, it is contingent upon a certain condition being met, a condition that we cannot verify or be sure about at first. But in spite of this, it can still be a valid argument or statement. A conditional statement starts with a premise that leads to a conclusion. If A is false is the premise, and then B is true is the conclusion. And the truth of the conclusion depends on the truth of the premise. If it is a valid argument or statement, and if the premise is true, then the conclusion will also be true. We don't know if A is false or true. There is no way to know that at first look. We are not saying that A is false. We are rather supposing that if A is false, then what? What would be the outcome of that? It is a supposition or a postulation, not a statement of fact. It may or may not be true. Maybe a better way to phrase this would be, if A were false, then B would be true. This gives it a sense of doubt, using the subjunctive mood, but that's not how we generally say it. The accepted phrasing of the formal definition of a strong link is, if A is false, then B is true. You simply need to be aware that it is a conditional statement and not a fact, okay? Like if I score 90% or higher on my chemistry test, I will get an A. This is a conditional statement. Getting an A depends on scoring 90% or higher. But before the test, we don't know what our score will be. Still, this is a valid conditional statement or argument. Or if my mother was a full-blooded kangaroo and my father was a full-blooded crocodile, I would be half kangaroo and half crocodile. Now, I'm pretty sure my parents were both human, but nonetheless, this would be another valid conditional statement. It is valid because if the conditions were true, then the conclusion would also be true. Here are the formal definitions for strong links and weak links, and as you can see, they are both conditional statements. For a strong link, if A is false, then B is true. And for a weak link, if A is true, then B is false. We use the letters A and B in the formal definitions for both strong and weak links in order to make it simple. But when we are constructing chains, you have to be able to apply this to multiple candidates or nodes, so they can't all be A and B. We have to think of A and B as being transient. For instance, up here in row 1, let's start on this 3 and call it our candidate A, and then let's make a link over to this 3 and call that our candidate B. And now we can say if candidate A is false, then candidate B would be true, and that is a valid statement, a valid supposition. There are only 2 candidate 3s in row 1, so if either one of them were false, the other one would have to be true, right? Because there has to be a 3 placed in row 1. This is a strong link. Are we all good on that? Okay. And now to continue with this line of reasoning, the next link in the chain must begin with this candidate B being true, because that is the conclusion of our first inference. Does that make sense? If A is false, then B is true. So to continue on from here and make the next link, which must be a weak link, this second candidate or node in our chain becomes our new candidate A, and the third node would then become our new candidate B, allowing us to say if this A is true, then this B is false, and so on and so forth. I mean, you could use all the letters of the alphabet if you wanted, and continue on with if B is true, then C is false, and then if C is false, then D is true, etc., etc. You get the idea. But for one isolated example, referring to only 2 candidates, and to learn this concept, it is much easier to always say if A is false, then B is true, or if A is true, then B is false. It's just a convenient generalization for any 2 particular candidates. Now that you are supposing that the second candidate of the chain is true, you cannot start the next link by supposing it is false. Thus, the only way we can logically proceed in the chain is to alternate the links, so that the second node of any link becomes the first node of the following link, with the same value for that node or candidate being true or false that was the result of the previous link. And the other thing a lot of people struggle with is the idea that we can use a strong link as a weak link, but not the other way around. You can never use a weak link as a strong link. It does not work, and it will not work. But here's why a strong link can act as and be used as a weak link. There are only 2 candidate 3s in row 1. They are a conjugate pair. This means that one of them has to be true and the other has to be false. That's the only way it can be. There has to be a 3 placed in row 1, so one of them must be true. This allows us to say if A is false, then B is true, i.e. the formal definition of a strong link. And of course, either one of them could be our candidate A. It will work either way. If the 3 on the left is false, then the 3 on the right would be true. And if the 3 on the right is false, then the 3 on the left would be true. But notice that we can also say if A is true, then B is false, right? Because if either one of them is true, the other has to be false. And this is the formal definition of a weak link. So you see, the definition of a weak link applies to a strong link. A strong link has the properties of a weak link and can therefore be used as a strong link or a weak link. So a chain could be constructed entirely of strong links, and it would still function as an AIC. And if you have been following my course and watching the tutorials in chronological order, You know that when I use a strong link as a weak link in a chain, I always refer to it as a surrogate weak link to differentiate it from a conventional weak link. Even though it is really a strong link, it can act as a weak link, if need be, to make our chain. And believe me, this happens a lot. But now let's take a look at a conventional weak link. There are 4 candidate 3s in column 9. So if we choose a particular one of those 3s and assume it is true, then all of the other 3s would have to be false, right? This is because there can only be one 3 placed in column 9 or in any house, i.e. a row, column, or block. Don't forget, blocks are houses too. Like if we assume that this candidate 3 is true, then this one would have to be false, and that would be a weak link. Or if we assume this one is true, then this one would have to be false. And again, that would be a weak link. We can choose any 2 3s in that column and say that if A is true, then B is false with confidence, because we know exactly one of those candidate 3s must be true and all the others must be false, even though we don't yet know which one is the true one. Any one of those candidates could be our candidate A, and any one of them could be our candidate B, and regardless of which 2 we choose, we can safely say if A is true, then B is false. That conditional statement would be valid. But with a weak link, you absolutely cannot say if A is false, then B is true. Because if we suppose that any one of those candidate 3s is false, you cannot possibly know which of the other candidate 3s in that house is true. This is why a weak link can never be used as a strong link. Got it? In any chain, if we need to start with the premise that a candidate or a node is true, we can always make a link from that node to any other node using either a conventional weak link or a surrogate weak link, as long as you follow the rules for links. And the rules for links are these. To link 2 same-digit candidates, they must both lie in the same house. And to link 2 different digit candidates, they must both lie in the same cell. And you cannot violate either one of these rules, or your chain will not make sense and you will not be able to draw any valid conclusions or make any deductions about it. And a quick word about making links within cells. The only way you can make a strong link within a cell is with a by-value cell. In a by-value cell, one of the 2 candidates must be true and the other must be false, just like when there are only 2 remaining instances of a particular candidate within a house. Like these are all strong links. But don't forget, these are not called conjugate pairs. The term conjugate pair is reserved for a strong link between 2 same-digit candidates. Like these are all conjugate pairs, the 2 3s, the 2 1s, and the 2 7s. But please don't make the mistake of calling these conjugate pairs. Even though there is a strong link between all those candidates within those 3 by-value cells, it is not technically correct to call them conjugate pairs. And if there are 3 or more candidates within a particular cell, then you can only make a weak link between any 2 of them, for the same reasons as when there are 3 or more instances of a particular candidate within a house. There is only a weak link between any of the candidates in this cell, like between the 1 and the 9, or between the 8 and the 2, or between the 4 and the 6. Between any 2 candidates in that cell, there is a weak link. And of course, in a by-value cell, there is both a strong link and a weak link between those 2 candidates because both definitions will apply. So you can always use the link within a by-value cell as either a strong link or a surrogate weak link. An AIC type 1 will always begin and end with the same digit candidate. Like if it starts with a 9, it must end with a 9, regardless of what lies in between, like you see here. And if every node in the chain is the same digit candidate, like you see here, this is called an X chain. as we learned about in videos number 14, 15, 16, and 27. So an X chain is an AIC type 1, but all AIC type 1s are not X chains. Like all cobras are snakes, but not all snakes are cobras. So with an X chain, there can never be any links within cells, because you could never have two of the same digit candidate in a single cell to link together. And just for the record, here in this diagram, these two circled 7s would be false because they can see both of the endpoints. But when an AIC type 1 uses an assortment of candidates, as they often do, there can certainly be links within cells like this. As you can see up here in row 3, column 2, there is a strong link within that by-value cell. And then there is a weak link between the 1 and the 3 in row 8, column 1. And there's another weak link between the 1 and the 7 in row 9, column 1. And there's a strong link between the 7 and the 4 in this by-value cell here in row 6, column 3. And just for the record, these 4 candidate 4s would be false because they can see both endpoints of this chain. Okay? And further, an AIC type 1 will always begin and end with a strong link and will therefore always have an odd number of links. As you can see here, we have 1, 2, 3, 4, 5, 6, 7 links. And by constructing it like this, it allows us to conclude that at least one of the endpoint candidates must be true, which further allows us to eliminate any same-digit candidate that can see both ends of the chain. This is the sole objective of an AIC type 1. The reason we know that at least one of the endpoint candidates must be true is because if the chain begins and ends with a strong link, we can run the logic backwards or forwards, regardless of which end we start on, and the chain will work and make sense. It will show that if either of those endpoints is false, then the other would have to be true. This ensures that at least one of those endpoints must be true. Let's look at all 4 cases for this chain. Now remember, we could call either one of those endpoint candidate 9s the first candidate because you can run the logic either way. But to demonstrate this point, let's start by calling this 9 up here in row 3, column 2, the first one, and this 9 down here in row 9, column 3, the last one, okay? So the first candidate is either true or false, and likewise, the last candidate is either true or false, right? These are the 4 cases. Our objective here is to prove that at least one of the endpoints must be true. So case 1 is that the first candidate is true. In this case, we don't have to go any farther. Case 1 satisfies our objective. One of the endpoints would be true. If it's true, it's true. We don't even need the chain, right? And case 2, if the first candidate is false, then the last candidate must be true because of the logical inferences in our chain. If this 9 up here in row 3, column 2 is false, then the yellow one would be true because that's a by-value cell and that's a strong link. So now if that yellow one is true, the blue one up in row 1 would have to be false. And if that is false, the yellow one over here in row 1, column 8 would have to be true because there are only 2 1s in that row. And then if that yellow one were true, the 9 would have to be false because that's a by-value cell. And then if that 9 is false, this yellow 9 would be true because that's a strong link. Those are the only 2 9s in column 8. Then we have a weak link over to this 9. So if the yellow 9 is true, the blue 9 is false. And finally, this is a strong link down to this yellow 9. So if the blue 9 is false, this yellow 9 would be true. So that proves if the blue 9 in row 3, column 2 is false, the yellow 9 in row 9, column 3 would be true. And again, case 2 also shows that one of the endpoints would have to be true. So now let's switch the chain and start on the other endpoint. It's the same thing. Case 3 would be that this blue 9 down in row 9, column 3 would be true all by itself, again giving us the desired result without having to go any farther. And finally, case 4 would be that this candidate 9 is false, proving that the yellow 9 in row 3 would have to be true because of the logical inferences of the chain. We don't have to go through it in such detail this time. If this one is false, this one is true, then this one is false, this one is true, that one is false. And by the way, that's a surrogate weak link because that's a strong link that we're using as a weak link. And then if this blue one is false, this one is true, this one is false, and finally the yellow 9 in row 3, column 2 would have to be true. So in all 4 possible cases, we have shown that at least one of those endpoints must be true. Case closed. And I say at least because in some cases, both endpoints of an open-ended AIC can be true. This is generally not the case, but it can happen, as I will demonstrate in future tutorials. There is what I call an effective strong link between those endpoints because if one of them is false, the other must be true. This is the formal definition of a strong link. If A is false, then B is true. This definition applies even though the two endpoints do not see each other. That's why I call it an effective strong link as opposed to a regular or conventional strong link, which is a direct link within a house or within a cell. Like here in this chain, there is a conventional strong link in column 3 between those two 9s, and there's a conventional strong link in the by value cell in row 3, column 2. And there is also a conventional strong link between the two 1s in row 1. But the link between the two endpoints is an effective strong link because of the chain of inferences. And it is only with an effective strong link that A and B could both possibly be true. In a conventional strong link, it is not possible for both candidates to be true. One must be true and one must be false. With a conventional strong link, you can say if A is false, then B is true, and you can also say if A is true, then B is false. But with an effective strong link, you can only say if A is false, then B is true, which satisfies the formal definition of a strong link. I know some of you may think that I'm belaboring this point, but you absolutely must understand all these things. In a conventional strong link, within a house or within a by-value cell, the two candidates cannot both be false and they cannot both be true. One must be false and one must be true. But with an effective strong link between the two endpoints of an open-ended AIC, the two candidates cannot both be false, but they can both be true. Most of the time in an AIC type 1, they will not both be true, but it's important for you to know that they can both be true, okay? It does happen. And in fact, it turns out that both these endpoint candidate 9s are true. There are too many steps left in this puzzle, and it would take too much time to solve it right now to prove that, so just take my word for it, okay? But with an AIC type 2, it happens much more often that both endpoints are true, as you will see in upcoming lessons, even though they are not necessarily both true. This is why, unlike all other Sudoku instructors out there, I make the distinction between a conventional strong link and an effective strong link. I think it's a very important difference, one worth noting and having a special term for it. But the one thing we know for certain, and without a shadow of a doubt, is that with an effective strong link between the two endpoints of an open-ended AIC, either type 1 or 2, we know that at least one of those endpoints must be true. Now, chains do not always have to begin with a strong link. We can start with a weak link if we want. And so here you could say that if the yellow candidate 1 was true, then the blue candidate 1 would be false. And if the blue candidate 1 was false, the yellow candidate 9 would be true, and if the yellow candidate 9 was true, then the blue candidate 9 would be false. So now we could say if this yellow candidate 1 were true, the blue candidate 9 would be false, and that would be a valid assumption or conditional statement. And we could also run this chain backwards and say if the yellow 9 down here were true, the blue one up here in row 1 would have to be false. But that would be as far as you could go because you have no idea which one of them is true. Being able to say that if the first candidate is true, then the last candidate is false does not help you or give you any conclusive information all by itself. With an open-ended AIC Type 1 or Type 2, we will never begin the chain with a weak link, okay? There are certain cases where starting a chain with a weak link can lead to valid conclusions when analyzed in combination with other information, but if we are trying to prove that one of the endpoints of the chain is true, we must always begin and end with a strong link. I hope that's clear. In closing, let's go over Sudoku Swami's 7 laws of links. If you memorize these laws, you will never make a mistake. Number 1. There is a conventional strong link between the last 2 remaining instances of a particular candidate within any house, i.e. a row, column, or block. Number 2. There is also a conventional strong link between the 2 candidates in any by-value cell. Number 3. There is an effective strong link between the 2 endpoints of an open-ended AIC. Number 4. There is a conventional weak link between any 2 same-digit candidates within any house when there are 3 or more instances of that candidate in that house. Number 5. There is also a conventional weak link between any 2 different digit candidates within any cell when there are 3 or more candidates in that cell. Number 6. When constructing an AIC, a conventional strong link can be used as a weak link if need be, and we will refer to this as a surrogate weak link. And number 7, you can never use a weak link as a strong link. All right, that's going to do it for today. If you enjoyed this video, please don't forget to click the red subscribe button and the thumbs up icon. And be sure to click on the little bell icon if you would like to be notified of any new video uploads. Now that we have a better understanding of strong links, weak links, and why the inferences in all Sudoku chains must alternate, in the next 4 lessons, videos number 34 through 37, we are going to fully examine all the characteristics of open-ended AICs, and I will show you some cool tricks on how to find and construct them. So I hope you will join me for all of that. In the meantime, be well and be happy.